Okay, first of all, let me thank Gabriel for this invitation. It's a great pleasure, and I'm very glad to give this talk here, this online talk at your differential geometry seminar. In this talk, I will talk about the concept of stability for extremal domains for the first Dirichlet eigenvalue of the Laplacian operator. This is a joint work with Marcos Petroso Cavalcante from the Federal University of Alagoas in Brazil. Let me give a quick introduction. If you consider M a complete Riemannian manifold, for each compact domain inside M with smooth boundary, I will denote by lambda1 the first eigenvalue of the Laplacian operator with zero Dirichlet boundary condition. So given n number between 0 and the total volume of the manifold, you can consider this first eigenvalue as a functional defined on the class of all domains with volume equal to M. So in this talk, I will be interested in the following natural question. What can we say about the minimizers, or more generally, the critical point of this functional? As you see, this problem is a type of isoperimetric problem. The first result in this direction is a famous inequality due to Faber and Krum, which says the following: if you consider a compact domain with smooth boundary and R in the Euclidean space, let me draw here a picture, and you consider a geodesic ball with the same volume, then the Faber-Krum inequality says that the first eigenvalue, the Dirichlet eigenvalue of the domain is greater than or equal to the first Dirichlet eigenvalue of the geodesic ball with the same volume. And the equality holds if and only if the domain is also a geodesic ball. In particular, this implies that in the Euclidean space, the only minimizer for this problem, for the first Dirichlet eigenvalue with this volume constraint, are the geodesic balls. So the global minimizer in the Euclidean space are completely characterized. And the same result also holds, is also true in the sphere in the hyperbolic space. About the existence of the global minimizers for this problem, let me present a recent nice result to do Lambolet and Perobert Stickbald, where and in this result they prove the following. They prove that for any compact manifold and for any volume between 0 and the total volume, you can always find a minimizer for the first Dirichlet eigenvalue. And this minimizer is smooth up to a singular set of dimension less than n-5. In particular, for low dimension, for example, 2, 3, or 4, you don't have singular points at the boundary. The minimizer is completely smooth. Now, a natural question is to ask about what we can say. What about the critical points of lambda 1 instead of minimizers? Let me first define precisely what we mean by critical points of lambda 1. So, if you have a compact domain with a smooth boundary in a Riemannian manifold, for any smooth vector field on this manifold, we have that the flow of this vector field generates a local deformation of the domain. You can consider this deformation here, omega t, given by the flow of the vector field. And we say that this local deformation is volume preserving if the volume of omega t is equal to the volume of the given domain for all t. So this is the definition of critical points of lambda 1, and we call critical points for dysfunctional extremal domains. We say that a domain, a compact domain with smooth boundary is extremal if it's a critical point of lambda 1 with this volume constraint, and this means that the first derivative of the derivative of the first Dirichlet eigenvalue is equal to 0 for any volume preserving local deformation like that. Okay, that's the definition. And the main tool to study critical points of the basic tool to study critical points of this functional is the first variation formula for this first derivative. Let me state this first variation formula. Denote by nu the outward unit normal vector along the boundary, and by phi the first positive eigenvalue of the Laplacian operator on omega with 0 Dirichlet boundary condition with this normalization. This is the first variation formula for this problem. We have for any local deformation of omega in M, we have that the first derivative of lambda 1 is equal to this integral along the boundary minus the integral along the boundary of V, where V is the normal component of the vector field that generates the deformation, times the normal derivative square of the first Dirichlet eigenfunction. Okay. That is the first variation formula. And the first basic consequence of this formula is the following. It's this to see that the local deformation is volume preserving if and only if the normal component of the vector field has 0 mean along the boundary. So this derivative is 0 for any volume preserved local deformation if and only if the first eigenfunctions of the Laplacian operator with 0 Dirichlet boundary condition has normal derivative, has constant normal derivative along the boundary. So this eigenfunction has to solve an overdetermined elliptic problem. We have that at the same time the eigenfunction has 0 Dirichlet boundary condition, and at the same time it has constant Neumann data on the boundary. Okay. Let let me present now some results about this type of domains. The idea here is that this overdetermined condition will imply several restrictions on the geometry of the domain. The first result is that one due to sharing, and this is a very important result. He proved that if you have a domain in the Euclidean space, and if this following overdetermined problem admits a non-trivial solution, that is, if this domain is an extremum domain, then the domain is a geodesic ball and the eigenfunction is a radial function. So in the Euclidean space, the geodesic balls are not only the only minimizer, but geodesic balls are the only critical points for the lambda one. The same results was proved by Kumera-san and Prajapa in the hyperbolic space and the open hemisphere. And the point here is that the important remark here is that the sharing proof is based on the moving plane used by Alexandrov to prove that the round sphere is the only closed CMC hypersurface embedded in the Rn. And another remark is that the moving plane method used by sharing fails in the whole sphere. It holds in the open hemisphere, but it fails in the whole sphere. To see that, let me present some examples of extremum domains in the sphere that are not geodesic balls. The first one in dimension 2 is this extremum domain that is topological and annulus. If you consider here the two sphere and in this sphere you fix an equator, so for it r greater than 0 or in less than pi over 2, we can consider two geodesic curves, circles, which are equidistant to the equator. So you have here an rotationally symmetric annulus that is an extremum domain. Another class of examples in S3 for dimension 3 are the domains bounded by the CMC Clifford tori. For NR, you can consider this tori in the S3. This torus bounds a domain, and this domain will be an extremum domain. And to see that these examples are in fact extremum, just note that they are part of this very general class of example. Every time you have a compact Lie group act on a manifold and a domain which is invariant by this group, then if the group acts transitively on the boundary, then this domain is extremum. The normal derivative of the first eigenfunction will be constant, since the action is transitive on the boundary. These two examples here, in the two sphere and the three sphere, both satisfy this condition. Let me continue by present some more results about extremal domains. The next one is this one to Packard and Stickbald, where they prove the existence of extremal domain in general Riemannian manifold. They prove that if you have a Riemannian manifold, and in this manifold, if this manifold has a non-degenerate critical point of the scalar curvature, then you can construct extremal domain with sufficiently small volume around this point. The same result is true without the hypothesis on the scalar curvature, and this was proved by Delay and Stickbald. And Stickbald then proved that for dimensions greater than or equal to 4, if the manifold has a non-degenerate critical point of the scalar curvature, then you can construct examples of extremal domains with volume extremely large, which will be complement of balls with sufficient small volumes. Let me say that these results due to Stickbald is still open to dimensions 2 and 3, and without this condition on the scalar curvature. The next result is this result to Stickbald and Schlenk, and they prove that it's possible to construct new examples of extremal domains in this product of the Euclidean space times the circle from the standard solid cylinder by using bifurcation method, and the same result was proved in the product of the hyperbolic space in the circle and the sphere in the circle. And recently, there is this nice result due to Ispina and Mazet, where they prove that if an extremal domain in the two-sphere is homeomorphic to a disk, then this extremal domain has to be a geodesic disk. And recently, Espina and Marin proved the uniqueness of that rotationally symmetric extremal analy in S2 among extremal analy with lambda 1 equal to, by assuming that the first the Dirichlet eigenfunction has infinitely many maximum points. Okay, let me now explain the concept of stability of extremal domains. This notion is very similar to the notion of stability of minimal surface and CMC surface. If you consider a Riemannian manifold in extremal domain in the Riemannian manifold, we say that this domain is stable. This extremal domain is stable if the second derivative of lambda 1 is greater than or equal to 0 for any volume preserving local deformation. For example, it follows from the Faber-Crane inequality that geodesic balls and the Euclidean spaces, the sphere and the hyperbolic space are stable extremal domains. In fact, they are global minimizers. And in our work, we note that the rotationally symmetric extremal analy in the S2 are unstable extremal domains. Let me present now the second variation formula for lambda 1 and consider again phi. Consider an extremal domain and denote by phi the first positive eigenfunction of the Laplacian operator with this normalization. So we have this following second variation formula for the lambda 1. The second derivative of lambda 1 is given by this quadratic form, where V, again, is the normal component of the vector field that defines the variation. C is a constant, which is the normal derivative of the first eigenfunction, and V hat is an extension of V to the following problem. And 8 here is the mean curvature of the boundary. So that quadratic formula defines the second derivative of the lambda 1. Let me press some remarks. The first one is about this extension, and this extension always exists because since the normal derivative of the first eigenfunction is constant, the Friedholm alternative implies that the extension exists if and only if the normal component of the vector field has zero mean, which means that the variation is volume preserved. And let me just remark that this notion of stability was first studied by Shimakura from a local point of view. And in this paper, he proved that local extremal domains in the Euclidean space is locally stable. And let me also note that Jorge and de Lima proved an index formula in this setting and used to prove an alternative to provide an alternative proof of Shikamura's results. Now let me give a consequence of the second variation formula for lambda 1. The first one is a direct consequence of the formula. Is that one? It's just an integration by part. The domain will be stable if and only if this inequality holds for any function on the boundary, such that this function has zero mean on the boundary. Note that in this part, we have this part here is defined on the extension of V. But in general, when you have a function on the boundary which has zero mean, in general, you don't know, you don't have much information about its extension. What we note in our work is that you can change this inequality by this one. This inequality here, this first inequality is equivalent to this one. An extremal domain is stable if and only if this inequality holds for any function defined on omega which has zero mean on the boundary. It's not necessary to consider just the extension of the functions on the boundary with zero mean. You can consider any function on the interior defined on omega which has zero mean on the boundary. So now you can try to find nice test function to use this inequality. Now let me present some our results about the stable extremum domains. The first one is the following characterization of stable extremum domains in dimension 2. We prove that if an extremum domain in the 2 sphere is stable, then this domain has to be a geodesic disk. And you can see this theorem as the parallel of the classical Barbosa do Carmo-Eschenberg theorem about stable symmetry compact hypersurface in space form. And a nice consequence of this theorem is that, together with the Lambolet-Thickbald results on the existence of minimizers, you can get an alternative proof of the Faber-Craig inequality in S2, because Lambolet and Thickbald guarantees the existence of a smooth minimizer, and our results characterize this minimizer. This minimizer has to be a geodesic disk. Our second result is the following classification of extremum domains in the n sphere for dimensions greater than or equal to 3, when the boundary of the domain is a compact minimal hypersurface. If in this case the extremum domain has to be an M sphere. Okay. In particular, the extremum domain in S3 bounded by the minimal Clifford torus, for example, is unstable. In fact, this information is not here in the slides, but we also can prove that other examples of extremum domains bounded by the CMC Clifford torus are also unstable. But this one follows directly from these results. And let me just note that it's an open question to prove that to characterize stable extremum domains in the n sphere for dimension greater than or equal to 3. We prove just with this condition that the boundary is a minimal hypersurface. Our next results are about topological control for stable extremum domains in Riemannian surface, general Riemannian surface. If we consider an orientable Riemannian surface, and in this surface we consider an unstable extremum domain, our first result is that if the domain has total Gaussian, non-negative total Gaussian curvature, then the only possible values for the genus in the number of connected components of the boundary are this one, or the genus of the domain 0 and with at most 5 bounded components, or the genus is 1 with at most 7 boundary components. And the next one is a result in the same spirit without this condition on the total Gaussian curvature, but instead this condition we consider only extremum domains with sufficiently small volumes. The only possibility for the genus is 0 or 2, and with at most 3 boundary components, and the genus is 1 with at most 5 boundary components. And let me say that our inspiration for these results comes from this beautiful paper due to Antonio Rossi and Aldo Vergasta, where they studied the stability of a hypersurface of constant mean curvature with free boundary and in convex domain of the Euclidean space. And let me remark that the study of determined problems using tools from the theory of CMC hypersurface was initiated by Ross and Seckbaldi in 2013 in the context of Berti-Caffarella-Nirenberg conjecture. Now let me give a quick idea of the proof. Let me start with the characterization of stable domains in the two-sphere. So consider a stable extremal domain in the two-sphere with R connected boundary components. First step is to note that for each unit vector in the two-sphere, this vector field defines a one-parameter family of rotations around the vector A. And these rotations are isometry of the two-sphere. So now we consider the first positive eigenfunction of the Laplacian with this normalization on the boundary. And when we define, now we define this function, we take the gradient of the first eigenfunction times the vector field, which gives the rotations. And the first observation is that this function fa has zero mean at each on each boundary component of the domain. For each boundary component you choose of the domain, this function has zero mean. And this follows from the simple computation. Now you note that since VA is a Killing vector field and the normal derivative of phi is constant, this function FA solves the following problem. And thus, since the domain is stable, it's a standard argument that if this function does not vanish, then this function is a second eigenvalue for this problem, this above problem, and this implies that this function has at most two nodal sets. That is, the complement of the zero set of this function has at most two connected components. So the idea now is to prove that it's possible to choose A in order to obtain that this function is identically zero. And the A is chosen in the following way. You take A equal to P0, where P0 is the maximal point, is the point where the first eigenvalue attains its maximum value. And suppose that for this value of A, the function fp0 is not identically zero. So since the gradient of phi at p0 is equal to 0, and the vector field vp0 vanishes at p0, we obtain that p0 is equal to the function fp0 vanishes at p0, and the gradient of this function is also 0. So the point is that this function has at least two nodal sets at this point, p0 because of that. Moreover, recall that this function has zero mean at all boundary components of the domain. So the function has at least two zero at each boundary component. And since the genus of the domain is zero, it's you can use a standard argument using the Gauss-Bonnet theorem to prove that this function has at least three nodal sets, which is a contradiction because the domain is stable. And we noted in the last slide that if the domain is stable, this function has at most two nodal sets. And the point is that here you have the domain, which is homeomorphic to a disk with some other disks which are removed. At each boundary component, you have at least two nodal lines intersect at boundary components. But inside the domain, we have this point P0, and at this point, you have at least two nodal lines here. So since these nodal lines has to meet another nodal line, you can necessarily divide the domain in at least three nodal sets, which is a contradiction. So this function is identically zero. Sorry?
One question.
Please.
Can you recall what is a nodal line?
A nodal line? A nodal line is some line where the function is zero. Is some the nodal set are the complement of the zero set, and the nodal lines are the boundary of the nodal sets. A nodal line is a line where the function is equal to zero.
Okay, thank you.
Okay. Now let me explain the proof of theorem 2. And suppose that you have an unstable extremal domain, and suppose that the boundary is a minimal hypersurface. Since this boundary is a minimal hypersurface, you know that the coordinate functions have zero mean on this minimal surface. So recall that in this case, you can use the coordinate functions as test functions in the stability inequality. Thus, the stability of omega implies that you have this inequality. So by sum over I, you get that the first Dirichlet eigenvalue of the domain is less than or equal to n. But now, in order to conclude the proof, we just use the following result due to Riley, which says that if omega has reached curvature greater than or equal to n minus 1, and non-negative mean curvature on the boundary, then the eigenvalue is greater than or equal to n with equality if and only if the domain is an hemisphere. So here the Riley gets the inequality in one way, and the stability of the domain gets the inequality in the another way. So you have the equality and the repeat. Now, let me use this last 10 minutes to explain quickly the proofs of theorem 3 and 4. The main ingredient of this proof are a classical and famous technique in this setting of stability, which calls the Hirsch trick. Let me explain. Consider an orientable Riemannian surface, and inside the surface, consider unstable extremal domain. And suppose this domain has a non-negative total Gaussian curvature. So the first point is to note that we can obtain a map, a conformal map from this domain to the unity disk, such that this map has Dirichlet energy less than or equal to 2 pi the genus plus the number of boundary components of the domain. So the Hirsch trick is a technique that says that you may assume that the coordinate of this. Sorry. Okay. You may assume that the coordinate of this map has zero mean. So you can use the coordinates of this map as test functions. When you use these coordinates as test function and sum over I, we get this following inequality. In the left-hand side, you have a topological quantity, and in the right side, you have this term here, which is non-negative, and this term, which is the total Gaussian curvature. So if the domain has non-negative total Gaussian curvature, you get that the genus of the domain is less than 2. Now to estimate the R, we use the Hirsch trick, but now in a different way. We first construct an orientable closed omega bar from omega by attaching a free table disk at any connected component. Now, omega bar and omega have the same genus, and now you use that you can always find an holomorphic map from omega bar to S2 with Dirichlet energy controlled by this topological quantity. So again, by the Hirsch trick, you can assume that the coordinate of this map has zero mean on the boundary, and we've defined phi 1, phi 2, and phi 3 as the restriction to omega of the coordinate of the psi map. We can use these functions as test function again, and using that and sum over I, we get the following inequality again. And now using the hypothesis on the total Gauss curvature, you can control the number of boundary components. If the genus is 0, you get that the domain has at most 5 boundary components, and if the genus is equal to 1, the domain has at most 7 boundary components. And in order to improve these topological bounds without the condition that the domain has non-negative Gauss curvature, and assume that the domain has sufficiently small volume, we now have to get a better estimate on this term here, lambda 1 times the area. And in order to do that, you use this following result to do, where they prove this asymptotically expansion of the Faber-Cramp profile, which gives by this function fk. For each m, the function associates the infimum of lambda 1 among the domains with volume equal to m, and they prove that as the volume n goes to 0, then Fk times M goes to lambda 1 goes to the first Dirichlet eigenvalue of the unit digit times pi, and this is greater than 5 pi. So using this, you have that we have that if the stable extremal domain has sufficiently small area, then lambda 1 times the area is greater than 5. So you can improve. You can improve that term. Here is the same inequality, and this inequality implies that the genus now is less than or equal to 2, and to get a better estimate on the number of boundary components, you use the Dirichlet estimate to estimate this term by 5 pi and get a better estimate here for the genus. So if we do that, you conclude that if the genus of the domain is 0 or 2, then the domain has at most 5 boundary components, has at most 3 boundary components, and if the genus is 1, the domain has at most 5 boundary components. Okay. So I think I'll stop here. Thank you for your attention and for the invitation.
Thank you. Let's thank the speaker, please. Thank you, Ivaldo, for your very interesting talk. So let's go to the questions. Someone have a question? Can you listen me?
Yes.
Is there some question?
I'll ask a question.
Okay.
Okay.
Early on in your slides, you said that for low dimensions, you knew that I think it was at least minimizers were smooth. Are there examples of non-smooth minimizers in higher dimensions?
Okay, that is a very, very nice question. We don't know any examples where you get a minimizer that is not smooth on the boundary. We don't have.
For critical points?
For critical points, for critical point 2, we don't have any examples of it is an interesting problem to find some example of minimizer where you don't have that the boundary is smooth. In fact, we don't know if that codimension of the singular set is sharp. We don't know. We don't have the same information like a minimal surface, for example. We don't have the same information.
Thank you very much.
Thank you. Some another question?
I have some question.
Okay.
First of all, thank you for your time and your talk. Very interesting. My question is, it's pretty general because do you know if some or all of these results change if you consider the conformal Laplacian instead of the Laplacian you use throughout the research? How much does these results may change?
Yeah, so I know that there is results about overdetermined problems for general elliptic operators, but I don't know any results in this context of consider the first eigenvalue of this a different operator as a variational problem. I don't know. Maybe I think it makes sense. It makes sense to try to investigate this, but I don't know any result in this direction.
Thank you so much.
Okay. Some other question?
In fact, 3 weeks ago, I gave a talk at IMPA in Brazil, and a person in the audience made the same question to me. The same question.
It's
exactly the same question.
It was me.
Oh. Because it's a very natural question.
Yeah, because it's very common throughout the theory to consider the conformal Laplacian. So
yes, it's a very.
It may be very interesting to see to what extent can we conserve these results.
Yes.
Thanks again.
Okay, welcome.
Okay. Some other question? I have a question also. What other ambient spaces would be possible to work with? Riemannian ambient space, what other option is possible to obtain some results, maybe, for the future?
Yes, maybe, but it has to be a different argument because this argument we use to classify stable extremal domain. I use in a very strong way all the symmetries of the sphere. But maybe using a different argument, you can get some results.
Okay, some other questions. I'm going to stop here the presentation, the video.